So this talk is going to be titled Paying It Forward, Documenting Your Hardware Project. It's going to be approaches that we take in documenting our particular hardware project using a software package that I wrote called lxsocdoc. And the hope is that even if you don't use the same tools that we use, you can use some of the same approaches that we use in whatever hardware projects you end up using. Now, undocumented hardware is bad. I mean, this is the most gratuitous slide on here because this is obviously very true. But arguably, undocumented hardware is a little bit more difficult to understand than undocumented software, because with software, you can at least look at the code and understand it in a line-by-line fashion, whereas with hardware, every line of your HDL is executed at the same time. So in addition to the lines of code, you also have this extra dimension of time to take into account. But the problem is it's super easy to do because you're prototyping, and so you write something and then you go on. So this talk is going to be all about how we can make it easier to write hardware that is documented both for us today and for us in the future. Now a little bit about me. We're going to be talking later this week with my colleagues Bunny and Tom Marble on a Betrusted project. But for the past year, I've been working on this, which is an embedded FPGA development board that fits in your USB port. And one of the interesting problems I've run into on this is there are lots of FPGA development boards out there where you're just given this blank slate to do whatever you want. Which means you don't have to really worry about the documentation of many of those modules. But I wanted to let people program this as a RISC-V core, which means I'm now in the relatively unique position of distributing an SoC, a system-on-a-chip microcontroller. And I was trying to figure out a way to describe what this microcontroller was to the customers, to make it as easy for them to get started as possible. Now, I know a lot of people in here are pretty technical, but how does this work with a normal microcontroller? For example, if you have an STM32 or an AVR for an Arduino, how do those chips get documented? Now, the answer is with reference manuals. This is just a snippet of the I2C driver from the Novena laptop project we did. We picked that particular chip because it is incredibly open. You don't even need to sign an NDA to get the reference manual for this particular chip. And there's a couple of things you can notice from here. On the left side, there are some diagrams describing the I2C state machine. And on the right side, you have just a table with all these register addresses. If we go to the next page, you can see this is an example of what a register description looks like. There's this diagram on the left, followed by an individual field documentation. And every register gets its own entry in this reference manual. Some registers have some additional information. For example, on the right side, these are some tables for the different timings that are possible for this register. And in addition to this sort of per register documentation, if you go to the beginning of the reference manual, you see there's additional notes, for example, on different variants of the chip, what you can expect when you are bringing it up. The bootloader might be documented in here, but there is an additional information, just free-form textual information besides this register mappings. Now, one thing I'd like to clarify is that a reference manual is not equal to a data sheet. This is just kind of a minor point, but when you want a data sheet is when you are designing the electrical aspects of it. So a data sheet generally refers to things like what is the frequency of it, what are the maximum voltages. When you're programming the software, that is usually when you're looking for the data sheet, which is going to tell you where the registers are, what the boot cycle looks like, what the memory map looks like. And another thing to note is these things are massive. The IMX6 reference manual, this is from that very first introduction page. You'll notice that the introduction starts on page 197. Everything before that is table of contents. And this thing is almost 6,000 pages long. So there's a lot of information here, and this isn't even all of it. If you go to the 3D GPU section of it, it's about 2 pages that basically say, yeah, this is closed, go download the Vivante reference manual to learn how to use the 3D engine. So these things are very complex, very thorough, and in fact, there's a cottage industry in the black market to sell reference manuals that are under NDA because they're so useful. Anytime you want to use a chip, the first thing you want is this reference manual. Now the question is, how are these built in a professional enterprise type world? Well, they generally use some very advanced typesetting software that has like pagination and all this to generate all this. And we don't necessarily want to be using Microsoft Word to be working on our documentation because it requires a whole team of people who do nothing but write your documentation. We are open source people. We like using Git and continuous integration. We like writing tools that help us generate this documentation because that makes it easier on us and it means it's less likely to be wrong. So, now that we're almost 7 minutes into this talk, what is this talk going to be about? I'm going to go into the motivation behind the lxsocdoc project. I'm going to go a little bit into about the Python HDL code that we use. I'm going to give a few examples about how the lxsocdoc can be integrated with LiDX. And then I'm going to go over some of the benefits of this approach. Now, as for the motivation, this is the badge from the Hackaday Super Convention this year. This is an FPGA development board. It runs a RISC-V, two RISC-V cores, actually. And when it was designed to use a lot of the standard industry practices. So one of the stated goals was they didn't want to use any sort of Verilog generator. They wanted to write pure Verilog and do it in the same way as they do it in the industry. And this is a snippet from the mockdefines.h, which again is very similar to what you would get from some sorts of professional chips. And it has this first comment up here, UART offset with a value, and this is a C preprocessor define. But it does have a relatively long comment block that describes what it is. So the documentation for this chip is this header file. And then down here, the second register is the data register, and they have, I mean, this is a delightfully long comment describing how this works. But this is a header file. And if somebody goes and changes the Verilog definition, they're going to have to remember manually to come back and update this header file. So again, this is very much how it works in industry, but I think we can do better. For the Betrusted project and for Fomu and for a lot of my other projects, I use this project called LiDX, which is a hardware description language written in Python. Now, to be very clear, it does not execute Python code in hardware. What you do is you run it, and it spits out Verilog code, or in the cases of NMeGen, it spits out a Yosis netlist that then gets sent to a synthesizer to place it on the FPGA. But it has this benefit in that it's super easy to create a system on a chip. And incidentally, it is actually powering the LCA 2020 video recording system. The entire, if you're watching this online, it's actually used on these devices. By the way, I forgot to mention this at the beginning. If you go to p.xobs.io/LCA2020 PIF, you can actually follow along on your device. And later on, in a couple of days, the speaker's notes will actually appear on the slide. Right, so LiDX is very powerful, and it is so good that they're using it here at LCA. Now, what does LiDX code look like? This is an example of the LiDX code. This is a GPIO out, and you can see it looks just like a normal Python class. You have this self.com that is combinatorial logic, and you have this CSR storage. So with these primitives, we just glue them together, and out pops a system on a chip. So I'm just going to do a case study here using the SPI bitbang module. This is an example of what the SPI bitbang module looked at when I first saw it. So when you have a serial peripheral interface, generally you treat it as a block of memory, but occasionally you need to do something more special, like erasing blocks of memory or switching between quad mode and single mode. And to do that, you generally put it in a special mode where you're writing individual bits. And in this example here, you could see aside from the fact that it's probably a little bit small, it's relatively difficult to follow because, for example, you have if self.bitbang storage bracket 3. What is storage bracket 3? I don't know. If self.bitbang storage bracket 1. I mean, these bits obviously have some information, but even just reading the code now, I have to have this code open, and I'm constantly trying to figure out what does this do. So I'd like some better way to document this. Now, the initial approach, we're going to use Python doc strings, which look like this, where you add this string block following a function definition. I realize that there's a fundamental difference between doc strings for the Python world and doc strings for the user world. If you are using these modules in your project, for example, in a Fomu project or in the Hackaday badge, then you are a Python user who wants to know how to use the Python interface. However, once this gets generated, this hardware might have different features. For example, this chip might have a touchpad, whereas that one has buttons. And you maybe want to have a class that dynamically has buttons or a touchpad, and they may have different register interfaces. So you would document the ability to switch between these register interfaces in the Python section, but this wouldn't necessarily give you information once it was all synthesized and elaborated. So we needed to come up with a better way to define the hardware. So we came up with this concept called CSR fields. So when you define your register like this is now the bitbang register defined. You could see it takes the first value is the number of bits of this register, followed by a list of fields. And this list of fields has strings like MOSI for Mozzie, for master out slave in, has fields like clock. Everyone has a full description. And then we have down here at the bottom, we have values. So for example, if this value is 0, then you know that that magic value 0 means out. And if it's 1, that magic value means in. So no longer are we restricted to doing lookups in the code in our head. Now it's all in the code. And additionally, there's a description on the bottom. And the thing is, these are so easy to make. So when you're making a new CSR, generally there's a comment that goes above that describes it. But if you do it this way, then you can put it in the definition itself, and it gets built along with the rest of your code. So if we go and refactor the SPI bitbang driver, it ends up looking like this. So the first line up there reads, if self.bitbang.fields.dir. That makes a lot more sense to me rather than storage bracket 3. That is obviously the direction bit. You could say down below it says it assigns something to self.bitbang.fields.mozzie. I mean, that's obviously the master out slave in. And these fields that are being used for documentation are now also being used for the code itself. So now that we have all this, we can actually go through and when we elaborate it, generate a full manual. This is the output. This looks pretty good, I think. This has that register schematic that we had from the professional documentation. It has some information above that describes what this register is. And it has the register fields down below, including, for example, the direction. You can see what the direction registers are. And this gets generated automatically. You can see LightX up at the top has picked the register address for us. This is a long way towards getting a full reference manual that you can actually generate a PDF for using Sphinx, which you can do to distribute to people. We could also go a bit further and generate and look through the interrupts that this SOC generates. And so this is an example of the interrupt controller being documented. You could see it's perhaps a little bit unintuitive that interrupts 0 and 1 aren't present, but that's just because interrupts 0 and 1 are usually the UART interrupts, and on this particular chip we didn't have any. But now that we have documentation, you can point out and say, interrupt number 2 is obviously timer 0, and you can click on it and then go see the documentation for timer 0. So in this way, we're kind of already better than those PDFs because we have automatically generated hyperlinks. Since we're doing an elaboration of the entire thing, we can even document some undocumented fields. So for example, the timer 0 module is a bit legacy, and it has no documentation for the interrupt events whatsoever. But you could see that it's pulled out the fact that this event interrupt is 1 bit wide and is called 0. And you can kind of imagine that maybe this interrupt fires when it reaches 0, just from that little bit of information. So it's undocumented still, but it's still given value that we're able to pull this out of the documentation. We can go a step further and use module doc to document a module ourselves by attaching an object to the object ourselves. And so this gives us an entire documentation. So when I first saw the timer 0 module, it had no documentation whatsoever, but you could see now this timer can run in 3 different modes: polling, one-shot, or periodic. This is complex functionality that was before you had to read the C code to figure out how it works. You can also document protocols. So this is an example of the USB Wishbone protocol documentation. This is a wavedrom file. And so when you instantiate the USB Wishbone bus with debug mode, this automatically gets added. So the resulting documentation is dependent on the features that you enable at compile time. Finally, is kind of, when you do this sort of thing, you can use this documentation to generate machine-readable descriptions. SVD is the system view description, which is an XML definition that comes from ARM. It describes a lot of things about the chip. When you get an STM32, they might send you an SVD file. It describes the registers. It describes the contents of the registers, what the fields are, what the interrupts are, and what the memory maps are. We can generate SVD files now that we have a complete listing of all the different registers in the system. And this means we can do a lot of really cool things now. There's a project called SVD to Rust, which we can use to generate safe accessors to the various hardware blocks. So we can take the SVD file that gets emitted by this build system and generate this call up here to modify an RGB LED. Now, the actual implementation is unsafe because it's doing raw pointer access, but it's wrapped around safe functions because it is impossible to put an invalid state using these Rust accessors. And all of these Rust functions are generated automatically by this SVD file that gets documented by us. For other projects, there's this really cool project we're using called Renode that is kind of like QEMU on steroids, and it will ingest an SVD file. So this is an example of the Betrusted project, which also uses lxsocdoc. And I generated an SVD file for that and fed it into Renode and was able to get the UI working. And you could see on the left there, it is actually pulled out these like I2C control, I2C prescale, SRAM ext. These are all unimplemented in the current Renode implementation, but it was able to tell me what the actual writes were and give them human-readable labels just by generating this SVD file. And so, to recap, the benefits of the higher-level languages, you can reuse code a lot, so we're able to reuse all of this Python modules across a bunch of different FPGA families. With these higher-level languages, we can give more hardware description. We can give more description to our hardware blocks. So if we were using Verilog, we'd be restricted to just comments on top of the constants that we use, for example, with the Hackaday badge. But with Python or Scala or some other high-level language, we can annotate our registers and get this ability to generate these SVD files afterwards. Once we have that, we can generate automatic documentation for both humans and for machines with the source of SVD. So once again, documentation helps others because once you have all this, you can give somebody the documentation and they can actually do something with your project. But to be a little bit selfish, documentation helps you 6 months down the line when you're looking at your old code and you don't remember what you did, but it also helps you immediately because now you can access fields by name instead of by index, and it helps keep all of this hardware flow in your mind as you're writing your hardware module. So, thank you. Any questions?
Hi. I think you just solved the problem I was facing like 3 months ago completely. Um, I have two questions, if you don't mind.
Sure.
You mentioned you can document serial protocols. Just want to, can you elaborate a little bit on that? I was wondering if you can document not just SPI, but just normal serial UART, RS-485, and that kind of stuff?
Yeah, so the actual documentation of protocols, for example, this protocol documentation is entirely written in Wavedrom, which is a wonderful package for generating, it's primarily for waveforms, but we also use it for generating the register fields. Wavedrom is a little bit difficult to use. The best way I've found to actually use it is to open up the Wavedrom example webpage. So it's entirely JavaScript, and you're basically feeding it a JSON file. And so the best way to do it is to go to the Wavedrom online editor and keep adding fields until it looks pretty enough. So there is a implementation of the Wishbone bridge I did called Spybone that tunnels Wishbone over SPI. And that one is interesting because the documentation changes depending on whether you're doing it in 2, 3, or 4-wire mode. And that just involves attaching different versions of the documentation to the object at compile time. And that basically uses pre-baked Wavedrom files that I did this approach where I went to the website and I typed in the definition and then copied it into the documentation that got attached to the output. So currently there is no sort of automated waveform generation. It's very manual, but it's very easy to do. So it's not too big of an issue to manually generate these waveforms.
And second question, in case, I hope, I came in late, so if this was already answered, is this like, do you need to be familiar with Python to generate this, or can you then auto-generate C and C# accessors, for example?
So the way this works, this talk has two approaches, two motivations. One is to let you know about this project, lxsocdoc, and the other is to let you know that this is an approach you can take to document your registers. Now I know that Sci5 has a similar approach they're taking where they actually, instead of documenting the registers and adding it to Scala, they actually have a separate file that does all the documentation, which I think kind of gets us back to the old method of having an Excel file or a Word file that describes all of your documentation. But having it in a documented format is really what you want to do. And if you're using a language like Scala or one of the other Python generators, then I think this is a very beneficial approach to keep the definition of your registers very closely coupled with the code you're writing to implement them. Thank you very much.